Good afternoon, everyone. Today, we're diving into the world of convolutional neural networks, or CNNs, a fascinating area within machine learning, particularly when it comes to image analysis. CNNs are a specialized type of artificial neural network, purpose-built to handle visual data. Unlike traditional neural networks, which connect each neuron to every other neuron, CNNs are designed to process data in a structured grid format, making them uniquely suited for images. So, what makes CNNs so effective at analyzing images? Well, they work by breaking down an image into its essential elements, detecting patterns like shapes, textures, and edges. Imagine looking at a photo of a dog. As humans, we instantly pick up on details like the shape of the dog's body, its fur texture, maybe even the sparkle in its eyes. CNNs operate in a similar way, beginning with simple pattern recognition in the initial layers, like identifying edges or specific textures, and then progressing to more complex features as they move deeper through the network. This layered approach is what allows CNNs to understand images in a meaningful way. Early layers might detect fundamental features like lines or curves, while deeper layers combine these elements into more recognizable structures. Eventually, the network can distinguish higher-level concepts, such as identifying a dog by recognizing the combination of ears, eyes, and nose in familiar arrangements. CNNs have made a significant impact across various fields, from powering facial recognition systems and medical imaging to driving advancements in autonomous vehicles and beyond. By structuring information hierarchically, CNNs emulate the human visual system's approach to interpreting images, which is why they're so effective at transforming raw image data into insights. So, as we move forward, think of CNNs as a way for machines to see and interpret the world, bridging the gap between raw pixels and meaningful information. Now, let's explore the core components that make up a convolutional neural network, what I call the building blocks of CNNs. These layers work together in a sequence, each with a specific role in transforming raw image data into something that can be interpreted by a model. First up is the convolutional layer, which is essentially the backbone of a CNN. Think of it as a filter, scanning over the image bit by bit. Each filter or kernel is trained to identify specific features within the image. For example, one filter might become specialized in detecting edges, while another might focus on identifying textures. As the model processes more images, these filters learn to recognize different parts of an object, whether that's a curve, a sharp edge, or a particular texture. The convolutional layer applies these filters across the entire image, creating a feature map that highlights areas where certain patterns occur. It's this ability to pick up on minute details that makes CNNs so effective for visual data. Next, we have the pooling layer, another essential component in CNNs. Once the convolutional layer has identified features, the pooling layer steps in to reduce the spatial dimensions of the feature maps. Imagine shrinking the image down without losing the key information. Pooling achieves this by summarizing region of the feature map, typically taking the maximum or average value in a small area. This process not only reduces the size of the data, but also makes the model more efficient and less sensitive to slight shifts or distortion in the image. By focusing on the most prominent features, pooling allows the CNN to maintain the core information while reducing computational complexity. Together, these layers, the convolutional layer for feature extraction and the pooling layer for downscaling, form the fundamental building blocks of a CNN. It's this combination that allows CNNs to efficiently process complex images, focusing on the essential details while discarding the unnecessary information. Now that we've covered the building blocks, let's talk about the key strengths that make CNNs stand out, particularly in tasks that involve visual data. CNNs have a couple of defining strengths that have set them apart as a powerful tool in image processing and beyond. The first strength is feature detection. One of the remarkable things about CNNs is their ability to automatically detect important features in an image without any manual input. This means that unlike traditional methods where features need to be predefined by a human, CNNs can identify relevant details on their own, which makes them incredibly well suited for handling large datasets. As the network is trained, it adapts to recognize various shapes, textures, and patterns that are important to the task at hand, whether that's identifying a cat in a photo or detecting abnormalities in a medical scan. This automation not only speeds up the process, but also makes CNNs scalable and versatile across different applications. Another crucial strength of CNNs is their spatial awareness. CNNs excel at capturing the spatial relationships within an image. For example, in a face, the spatial relationship between the eyes, nose, and mouth is critical to understanding it as a face. CNNs preserve this structure through their layered architecture, allowing them to recognize complex patterns in objects with an understanding of how these elements are positioned relative to each other. This spatial awareness is what enables CNNs to interpret images with intricate structures, such as recognizing faces, identifying objects in a scene, or even interpreting handwriting. These strengths, feature detection and spatial awareness, allow CNNs to take on tasks that require nuanced understanding of image data. This capability has paved the way for CNNs to be applied in various fields, from facial recognition in social media to autonomous driving, where understanding the spatial relationships in a scene is critical for safe navigation. Let's take a look at some of the real-world applications where CNNs are making a tangible impact. CNNs are transforming industries by enabling machines to interpret images in ways that were once only possible for humans. One of the most well-known applications of CNNs is image recognition. This includes areas like facial recognition, where CNNs analyze facial features to identify or verify individuals, a technology widely used in security and social media platforms. CNNs are also critical in autonomous driving. Here, they help vehicles see the road, detecting objects, pedestrians, and traffic signs to ensure safe navigation. In security, CNNs are deployed to monitor and analyze video footage, detecting unusual patterns or activities. In medical imaging, CNNs are proving to be a game changer. Medical images like X-rays, MRIs, and CT scans contain vast amounts of data that require careful interpretation. CNNs assist by detecting patterns that might indicate diseases or abnormalities, helping doctors make faster and more accurate diagnoses. In some cases, CNNs can even spot details that are difficult for the human eye to catch, offering an additional layer of precision in areas like cancer detection, where early and accurate diagnosis can be life-saving. CNNs are also making waves in retail and fashion. In inventory management, CNNs help retailers track and organize products more efficiently by recognizing items in real time. For fashion recommendations, CNNs analyze customer preferences and patterns, suggesting products that align with an individual's style. And with the rise of augmented reality, CNNs allow customers to virtually try on clothes or accessories, enhancing the online shopping experience and bridging the gap between physical and digital retail. These real-world applications of CNNs are just a glimpse into how this technology is shaping the future, from improving our safety and health to personalizing our shopping experiences. The versatility and precision of CNNs continue to drive innovation across a diverse range of fields. To conclude our exploration of convolutional neural networks, let's look at where CNNs are headed. With rapid advancements in artificial intelligence, CNNs are not only improving but expanding their reach far beyond traditional image processing. Researchers are pushing CNNs to handle even more complex tasks, such as processing videos and 3D data. This evolution is opening doors to new applications, like understanding dynamic scenes in real time, which has powerful implications for areas like augmented reality and interactive media. We're also seeing CNNs integrate with other AI technologies, like natural language processing and reinforcement learning, creating more sophisticated systems that can analyze and understand complex environments holistically. Imagine a future where CNNs, combined with other AI tools, could help autonomous systems understand entire scenes in ways that allow for better decision making. whether that's navigating crowded city streets or assisting in medical surgeries with real-time guidance. The future for CNNs is filled with exciting possibilities, and as they continue to evolve, they'll undoubtedly push the boundaries of what's possible with visual intelligence. Thank you for joining me on this journey through CNNs, and I hope it's given you insight into the profound ways this technology is shaping our world.